Hello, everyone. Good evening. Welcome back to our third day of the workshop. As you all know, we're back with Engineer Amr. Please write your questions in the chat box, and when possible, Engineer Amr will discuss them. We can get started. Thank you.
Yeah. Hello, everyone. Again, Samra Labib. That I will start the third day, and I'd like to recap what we got in the yesterday and the day before. So, if anyone didn't see the videos, I recommend to go and see the first and the second video, or this first and second day. The first day we talk about the reservoir engineers objectives and department integration with reservoir engineers like G&G, production technology, drilling and business units and all of that. And then we have an overview about reservoir simulation. And we ended with the terminology of IFS, integrated field study. What does it mean? And reservoir static modeling overview. We discussed or explained with each other or the structure modeling, petrophysical modeling, fishes modeling, and we agreed that in the structure modeling there is some uncertainty in making the horizons and zones and layers and respect to the resolution of the wells. And in fishes modeling, the how we distributed and the property modeling, of course, like the same. And then in the second day, we explained with each other and I want today to be more interactive. So we agreed that the dynamic model workflow will start with the initialization, and the initialization have inputs like scal, and today we will discuss the PVT and all of that. And we focused in the initialization that the first thing in initialization we will see the dynamic volume and compare it with the static volume to see if there is a deviation or not. And finally we discussed the rock physics, and we saw that we have a homework to do or task to do before we insert the rock physics as a relative permeability and capillary pressure curve in the initialization before running the simulation, and the effect of the relative permeability and how the model can read this curves. I don't need to put a massive number of curves, only one curve that will be normalized, and then the model will denormalize again, and depend on the endpoint scaling, he will the model will distribute the relative permeability curves again for each rock type or each lithology that in fishes modeling. And finally, we discussed the interfacial tension and how it affects the wettability and the capillarity in the model. And we have homework to do that we have the capillary pressure curves and convert to, and we discussed the lever J function to have a capillarity in each rock type with or each cell that have permeability and porosity that differ. And we converted the R to root permeability over porosity. All of that we have made, and today we are going to discuss the second thing in the that is crucial in the also in the modeling in the modeling initializations, that as fluid properties and PVT, and how it will affect. And here we will see the massive number of calculations that the simulation do to have the final product as a history match, and how it will get these properties, and to understand the phase behavior and the composition change with time steps and pressure decline. And after that, we will going to see the dynamic modeling, common challenges and solution. Again, we will talk about grid upscaling, something called LGR, local grid refining. How we will have an overview about components lumping and delumping, and how it affects the model and why we need to make lumping and delumping. Then for the composition, then we will have a slide for the project management in reservoir simulation studies. Finally, we will have a case study, and then question and answer like every day to or all over the workshop. So you, if you have any questions, please ask, and I will answer as much as I can. Okay, so again, like every day, all models are wrong, but some are useful. You saw yesterday and the day before that we made a lot of normalization and averaging and methods in distribution. So all of this is calculated calculation. So we are trying to do a model that is useful. So this is the slogan that we all agreed about. And also, we have to make a model with the scope of work. The first thing to do in the model is to know the target of the model that we are doing. What is the scope of work of this model? And you have to be you have to keep this model simple and clean and controlled and realistic. So this is our target in reservoir simulation modeling. So I will go through the second part in the initialization, the fluid properties. Simulators solve the flow equation, and yesterday we discussed the diffusivity equation that depend on the continuity equation or the mass balance equation and Darcy velocity rule. Here for the fluids, this or this continuity equations depend on fluids that could be oil or gas, and of course we have formation water. So each fluid has phase and volume behavior that change with pressure, temperature, and composition. So here we have another play, another game that with pressure change mainly. Of course, the reservoir is isothermal, it has one temperature, but if the flow goes through the well, the temperature is changing, so the fluid behavior will change, of course. But here we are focusing on the reservoir. So when the pressure decrease, uh, various variable will many variables will change with pressure. So this is a very it's a significant number of calculation will add in the simulation model. So that's why in the beginning I insist to tell you that we have to make the minimum cells that is mimic the real geology of the field, because of all the equations that the simulator must solve. So you will find here in the fluid properties, here at this picture as an example, at the right hand side, we have this picture, and in the right hand side, and in the left hand, you will have this picture. So the fluid, we have many type of fluid like volatile oil or black oil, or in the other side dry gas or wet gas or dry or gas condensate. So as an example here in this picture, if we have the A here, so if we are agreed that the reservoir is isothermal, so this is a gas condensate. So when the pressure decline, the condensation will happen in the reservoir. But as an example B, here the if the pressure declines, so it will remain in the gas phase. But if it goes through the well and then condensation happens, so in this time we call it wet gas. So this is the difference between the retrograde condensate and wet gas. So the condensate, gas condensate, the liquid phase formed in the reservoir, but the wet gas, the condensation happened in the well, not in the reservoir. And of course, if the reservoir is at this condition, which, as an example, 50 or 70 degree Fahrenheit and 3,500, so it will be in the oil phase, so it's oil well. So if you see the difference between the two pictures, you'll find this shape of the phase or the PT, and the PT diagram is different. You will find here the bubble line and the dew point line until the temperature, which here we call it Cricondenturn. That is the maximum temperature here. So you will find the fluid, each fluid will have a shape like this that can explain the liquid to the gas percentage. So here, if we have the bubble points, if we have here in the liquid phase, then the bubble will start at this condition, and then when the pressure decline, gas will evolve, and then 80% to 40% and 20%, and then it will decrease like that. So each fluid will have a behavior with the shape in the PT diagram. In the other picture, you will find another fluid that with this shape. So maybe at the temperature, as an example, 70, and the pressure 3,700 here. So it's a gas phase. But if we go down, the condensation happen. We call it gas condensate. But if the reservoir condition here at the 3,500 psi and more than 150 degree, so it will be in the dry gas phase. So the reservoir, the fluid is depend on the composition itself, come from biogenic or thermogenic gas, or according to the source rock and how the maturation of the hydrocarbon made, and the reservoir condition of pressure and temperature. So we have both two conditions that affect the reservoir fluid behavior that we have. But the bottom line here is when the pressure change, reservoir composition or reservoir behavior, fluid behavior will change. So as yesterday we spoke with each other, and I explained to you, when pressure decline, with the pressure, the saturation will change, and when saturation change, the relative permeability change, and the simulator need to calculate this. Here in the fluid also, when the pressure change, the behavior of the fluid change, and the challenge here is to mimic the fluid phase behavior, it change with the pressure. So I will start with this experiment here. This picture, you will find it in the WikiWitson, which is a very fantastic website I recommend. It's called constant composition or constant mass expansion. As agreed yesterday, that it's about mass continuity equation, or a conversion of mass. So mass in and mass out. So here, the first experiment that we have done in the lab, called constant composition or constant mass expansion. That if you see this animation, beautiful animation, that we are closing this valve and removing the piston down. So at the same temperature, which is reservoir temperature, I decreasing the pressure. So when I decrease the pressure, what happened? You will see the red is the gas and the green is the oil. So at certain time, at certain point, what will happen? The first bubble will come out. So from this, I can calculate with pressure what will happen. Where is the saturation pressure exactly? At which pressure we have the first bubble. So exactly what I'm doing is that here the fluid, and I start to decrease the pressure until the first bubble will come out, and then the gas will go again as to reach the 40%. liquid, and the gas is the rest. So this is the experiment that we have do. This experiment aim is to get the saturation pressure and also something called relative volume. As I mentioned yesterday, that the density, or as you know, we all know that density equal mass per unit volume. So we have a mass that of course, before this CCE, we have the fluid sample and inserted in gas chromatograph. So we have a detailed composition of the fluid. We can calculate the mass from it by something called molecular weight, and then we will see the number of moles, and then we have here the mass. So uh, when we have the mass, so the volume is at the saturation pressure, the relative volume is equal 1. So what is the relative volume? The second thing we know from CCE, it is the ratio of the of related volume to the volume on its pressure, saturation pressure. So in this relative volume, we will get the mass over the relative volume. So I can expect or calculate the density at each pressure. So the mass with the density will be equal the mass per unit relative volume. Related to what? Related to the volume at the saturation pressure. So we have these two variables. And I will repeat it many times. If the continuity equation you will have, you remember that we need to know the density of the fluid and the viscosity of the fluid, the main key uh, variables in the continuity equation. So here in the CCE we have the constant mass. So we will not going to produce the cell. It's constant mass, but divided in by the relative volume. So I can see the density at each pressure above and below the bubble point. So in this, the CCE, you will find that pressure, of course, measure the temperature, cell volume, relative volume. All of this, the relative volume is calculated as I mentioned, and the bubble point, we see it. We can calculate the density as I explained. And of course, we can use the equation of state to get the Z factor, something called Z factor for the gas and the gas saturation, all of that. But if anyone as an example in company interview or something tell you CCE, we know what the important or the primary things we know from CCE, you will tell him relative volume to get the density, and of course is the saturation pressure. This is the main target. So after that, in the lab also, we have the second experiment, but in this time, in this cell, we make another step. If you see here, we will have the but in this animation of the DLE, we decrease the pressure as you see, but I think the animation here is not correct 100%. We will produce the gas that is it will come out, and from this differential libration expansion we can get the GUR and to measure the Z factor and make the analysis of the fluid that we have. It's like the simulation is like we mimic the behavior of the reservoir production. So why I'm telling you all of this? Because in the reservoir simulation, with the pressure decline or in the continuity equation, when it is when the calculation happen, we have to know the some fluid properties changing, like the formation the formation volume factor, and the dissolved gas, and the viscosity and the compressibility, as you remember yesterday. So we got all of this data and inserted to the dynamic fluid model that we have. So in the oil, we are concerned about this variable. In the gas, concerned about the gas formation volume factor and the viscosity of the gas, and the Z factor. The Z factor, who don't know, it is the deviation factor, which is the deviation of the gas compressibility as a real gas from the ideal gas. As an example, in the ideal gas, we assume if the pressure compressed to two times, so the volume, of course, will decrease by half. But this happen not happening in the if the pressure increase two times, so the volume will decrease by half. But in real gas, will not happen. What will happen that if you multiply the pressure by two or doubling, so the volume will not going to change by half. It will change by half plus some fraction. So this is the deviation. It depends on the compressibility. I'm trying to simplify it as much as I can. So all of this, and also in the formation water, we are concerned about the formation volume factor of water, which is maybe could be one, and the compressibility of water, which is very low, can be negligible. But as an average in the standard, we assume it like 2 times 10 to the power -6, something like that. And the viscosity of water, it will be 1. But here the all of this is changed with pressure. So it must be at each time step, at each pressure decline. The simulator need to depend on the mass or continuity equation and the diffusivity equation. All of this change from time step to time step and from cell to cell. So you can imagine the numbers of the huge number of calculations that happened. And here we are going to discuss the difference between two simulators, something called the black oil model and compositional model. And it's not because it's called the black oil model, so it's for oil. No, it's for the one phase, even oil or gas. But the kind of or the type of simulator we call the black oil model. So black oil model, we use it in case we have one phase fluid in the reservoir, like dry gas or black oil. We can use this model. The model is depend on the schedules that I inserted from the CCE and the DLE differential libration expansion experiment. So the model will have its pressure decline, and from the new pressure it will get from this schedule, like the capillary pressure and relative permeability that discussed yesterday, this the formation volume factor and the viscosity and all of that. So it's a normal inputs. But in the compositional model, we use something called equation of states. It's another a very big title, but you can also don't keep it complicated. It's simple, but you need to understand it very well. Maybe in the future we can discuss it or make a webinar about it or something. But compositional model use equation of state. Why? What is the aim of the equation of state? We will see in the next slide. It will be more detailed. Something we can use it in the gas condensate or volatile oil, but it's very popular in gas condensate reservoir. That is the properties as a function of pressure and temperature. Why do we need the equation of state? We need the equation of state as a reservoir fluid mixture of many hydrocarbon components like methane, ethane, propane until C7 plus or C10, maybe C14 or 15. So when the pressure drop, what will happen? These components you will see that these components will change with pressure. So as an example, if we dealing with a gas condensate, so at reservoir pressure 4,000 and the dew point of this fluid maybe at 3,000, so you'll find the components of methane will be much higher. But if we reduce the pressure to 3,000, so the first dew or the first condensation will happen, and you will see that the components of methane or ethane will decrease, and the mole percent or the percentage of the C7 plus will increase. So the composition will change with time. So the simulation will calculate the number of the calculate the this concentration, and you will see or the percentage in each component, and we have by equation of state the final product, the percentage of phases that in each cell. So again, for the black oil simulators, it's a normal schedules that we got from the lab, from the experiments that I showed to you, from the DLE and the CCE. That the CCE, we are agreed that the cell is closed, we will not going to produce, so we have the constant mass, but we will know the saturation pressure. And for differential libration expansion, the DLE يعني the animation, I'm sorry, it's not right. In the DLE we produce, so the mass is not constant, and so the difference is that we mimic the reservoir behavior in production. So we will produce this gas, and then we'll make a total we will analyze this gas and see the gas oil ratio and the density of the gas and the compressibility factor of the gas, and we have all the data. We took this data and insert it in any simulation by very simple way. At each pressure, the GOR will be equal what, and the Z equal what, and the formation volume factor and all of that. And then we can run the simulation, and it will at the certain pressure, at each pressure, it will get from the schedule, the lookup tables, this variable. But what about the compositional simulation? The compositional simulation, as I mentioned yesterday, it's a very we are dealing with very massive equation solving. So in each time step or each pressure, we have a lot of variables that changed. The input of equations we made at the homework before we made the model, or I have to insert some parameters you will see in the next slide. The input will be the pressure and temperature and the composition of the fluid in each pressure and temperature. And the equation of state, the some functions will calculate, will calculate how many phases exist. It will be in one phase or two phase, depend on the pressure and the components, and how much the liquid versus gas, the composition in each phase, and the density of each phase. Because as mentioned that in the mass balance equation, the density and viscosity is very important. So without equation of state, we cannot correctly model the gas condensate, volatile oil, miscible gas injection, and carbon dioxide flooding. What is miscible gas injection and carbon dioxide flooding? As an example, in the enhanced oil recovery, sometimes the enhanced oil recovery, of course, it's simply the kind of the tertiary recovery that we use after the improved oil recovery or the second recovery. If we have some unmovable oil, so we will start to make water injection, so we can sweep the oil until we reach the irreducible oil or residual oil saturation. To get this residual oil saturation, we will change in the physics of the fluid. If as an example, the fluid is very thick, or if it's a very heavy oil, as an example, we will have try the steam injection. If we have if the water mobility is higher than the oil, we will make a polymer in the water, so we can alter the physical properties of the water, and increasing the viscosity of the water, so it will affect or sweep the micro sweeping, and then the oil will come produce the residual oil. But in the third part, called immiscible or carbon dioxide flooding, in the light oil, like maybe we can use gas injection in the condensate reservoir, or if we have a light oil, very light oil that is irreducible or residual, we will inject the carbon dioxide. It will dissolve in the oil. That's why it's called miscible, and it will never dissolve if the oil content, it will be the measure will be C5 and C6 and C7. So in that we need a compositional uh, reservoir simulators, so we can simulate the miscibility of the carbon dioxide or lean gas in the light oil, and changing in the viscosity of the oil, and then it will come out and produce. So that's why in the beginning I'm insisting to know the scope of work of any reservoir simulation. If reservoir simulation is concerning the geology, so focus on the rock types and focus on all of that. If the challenge that we have in the field, but if the challenge and they have in the field is the UR or gas condensate reservoir or something, so we need to mimic the change in the composition of the fluid and use the compositional simulator. So the equation of state, what are the equation of state? The equation of state, it's a function that, or equation that you can go and look for it, but I can help you to that the two most popular equation called called Ping Robinson equation, and Soroff-Redlich-Kwan, it's a SRK equation of state, called the cubic equation of state. So this equation of state, it's an equation. The input of this equation is the composition and some called centric factor and binary exponents and all of that. It's like another. It's an equation that you can give it an input of composition and some variables, so it could tell you the phases in the reservoir at each pressure simply. So the third part, as an example, in the gas condensate reservoir, not the oil. Here we have a gas condensate, the CVD, constant volume depletion. We also here have a gas reservoir that we will, as you see in red, and then we are going to decrease the pressure. So the first dew or first condensation will happen. So we have the saturation pressure here, but not a bubble point, it's a dew point. And then we will, after that, we will open, like you will see here, okay? It's like the DLE, but here the gas. We will open, so we got the oil and gas, and analyze in each pressure or each pressure step. We will analyze this composition. So by CVD, we can have this table at each pressure. As you see, we have the composition in mole percent. It will have, it must be 100% from C1 to C7 plus, but it could be until C25 or C30. So see the huge difference that happen in the fluid across the pressure depletion. In each pressure, the composition it changed totally from in term of mole percent. So, and then the gas also, we can took it and from the gas equation, the real gas equation, that PV equals Z nRT. So you can, from this, it's another mass balance equation. It's another topic in the PVT, but you can here estimate or measure the or calculate the deviation factor, that Z, that's very important in volumetric calculation, or the volumes dynamic calculation, that's Z. So here I will not, I'm trying also to keep it simple. So I need you to understand how the simulation understand or can translate the data to phase and phase percentage. It's like our brain, but it must it think by his own way. Actually, for us, there is something called Gibbs phase rule. It's a very simple rule. This rule is called it's as you see, F equals C minus P plus 2, where the F is the number. It's called the level of freedom, but Frankly speaking, I will tell you what is F. F is the number of parameters that can express the fluid. And the C is the number of components that we have in the fluid, and P number of phases. So we don't understand. I know that you are not understand. So I have it here schedule that will simplify things for you. As an example, if we have one component as methane, so C equal 1. And we have the phase, the methane is in gas phase. So we have one phase. Okay, if we have one phase of gas, methane, so the component equal 1 and phase equal 1. So to describe, to know the which component in the reservoir, we must mention two parameters, the pressure and temperature. Okay, it will be clearer in the next example. If we have one component like water, H2O, and the water is in two phase, vapor and water phase, liquid and gas phase. So when I say something like that, so we all know the boiling point is 100 degrees Celsius. So when I say that I have water, when I say that I have water in the boiling phase, so in the vapor phase and water phase, so it's by logic you will know that the temperature is equal 100 degrees Celsius. So the other variable will be the pressure. So it depends on the phases and the component. Another example, when I say that I have, as an example, one component H2O, and this H2O is in three phases. Could it be happen? Yes, it could be happen. There is a certain pressure and temperature. I think at 37 degree, 37 Fahrenheit as an example, and 0.018 psi, you will find that water could be in the three phases with each other. So when I said that I have a component, it is in ice and water and vapor in one phase. So already automatically I know that the pressure it will be, and the pressure and temperature will equal certain figure. So here another example. If I have a composition, this composition of methane and ethane gas. So I have two components, and the two components are in gas phase. To express this fluid, I must have the pressure and temperature and mole percentage of methane or ethane. So if I have methane and ethane as an example in gas phase, so I have two components. To express the components of this fluid, I have to say that I have a fluid, methane and ethane, at pressure equal what, and temperature, and the mole percent of ethane is 50%. So automatically the methane is also is 50%. So to express the components, it depends on the number of the number of components we can express the fluid. Okay, this is called the Gibbs phase rule. To express any fluid, we have to mention the variables. Okay, so in equation of state, the equation of state as a Ping Robinson or SRK, what equation of state do? The equation of state do that I inserting the composition like this, and according to this mole percent in each phase, in each pressure, according to the mole percent of each component in each pressure, the equation will calculate the percentage exactly of the phase. So as an example, if I am over the dew point pressure, so these components will be translated by the equation of state and tell me it's in one phase. But if I go the pressure decline, so it could be in two phase by, as an example, 30% gas and 7% oil, or vice versa. So this is the equation state do. They calculate to simplify things, calculate the number of components that I inserted and tell me the phase percentages of gas or liquid with each other. So This is how the equation of state do in the compositional reservoir simulators. I recommend to have, okay, I will do the numerical simulation, how numerical simulator works, and something called iteration, and then we will have a break. How numerical simulators work, yesterday we talked about it, that we have cells here, and each block have average pressure, saturation, and density, and we all know that from the two days before. And we have analytical term that we are agreed about, the accumulation that in a form of change of time, and the flux, which is called the storage, and the mass flux that depend on the Darcy's law, and then translated from analytic numerically to transmissibility multiplied by the mobility, and which is permeability over the viscosity, and delta P in I and J and K for each fluid. Here we are talking about fluids. As an example here, we are putting the pressure of water. So to get the pressure of water from the capillary pressure, I can expect the pressure of water as a wetting phase from the pressure of the oil as a function of the capillary pressure. So in each fluid, we could have its own flow equation. So here the again the oil balance and all of this. So here I'm trying to give you an example how simulators calculated. Simulator use iteration. Iteration means trial and error until the error will be zero. I need you to imagine a cell. If any cell in the model, the input of any cell in the model will depend on the output of the cell in the neighbor. So each cell don't know exactly at this time step, don't know exactly the input data. So how the simulator works? It's very simple. If in any equation I have input x and y, and it will give me output. But in reservoir simulation and cells, it don't know. Actually, in each cell don't know the input that it will have. It depends on the output of the neighbor cell, and etc. And this cell will depend on the input. So the simulator work as something called iteration formula. And the iteration formula, it's a very simple also. The P nu, the pressure nu of the cell of the new cell, will be equal the pressure that the input divided by the pressure of the old, divided by minus the pressure of the old, divided by the differentiation of the. As an example, I need to make this in number to be clear. If I have as an example a function of pressure, is it equal pressure, the old pressure, to square minus 4. So it's obvious that the pressure will be equal to, okay, it's a very normal function. P square minus 4 equals 0, so P will be equal to. Does the simulator work like this? No, because simulator don't know exactly what is the value that it will get. It depends on the other, the neighbor cell. So it must be iterate. As an example, if the cell, if the neighbor cell give it an input like 5. So what simulator will do? It will do an iteration. So the function of 5, it will be 5 square minus 4. It will give me 21. And then at the 21, and I will get the differentiation, or the derivative of this function. It will be 2p, p squared, it will be 2p, so it will be 10. Applying the iteration, or this rule, finally the p will be equal to 2.9. And then it will again iterate, make another iteration. You see the in the down. So 2.9, this one will be the old one will be minus the 4.4 over the 5.8, and give me at the final. I will repeat it many times until I will got 4 minus 4 equals 0. So again, we will make it, the simulation modeling will make its iteration. So the first one will be 2.9, as I mentioned here, and then this 2.9, it will be the old, and the new because the sorry, and the function of the old that you will put here, the 2.9 square minus 4 over the derivative, it will get me 2.14, and it will get the 2.14 as the old, and then make this iteration until we have this 2, and trying to make iteration for 2, it give me error 0. So the cell here will know that the answer is 2. So for us as a human brain is very simple, but for simulators it's not simple, because actually the cell didn't know doesn't know what number of input it will get, the figure that it will get, so it must be iterated. So imagine how many iteration in each cell in each continuity equation. That's why I'm telling you that we have a lot of calculation happen in reservoir simulation. So that's the example that I told you, that the first iteration at the pressure guess, it will be 5, and the after the iterations it will know that the exact value that must be make the new calculation about is pressure equal to, as an example. So I know that the speak in this topic is very full of details, and I'm sorry for that. But this is how simulation works, and the how phases or components change with pressure. So I think we could have a 5 minutes break, and I promise you the next session, or the next section of after break will be much easier.
Hello, should we ask question later or now? If I don't know.
Sorry, because I was muted. You can ask it after the 5 minutes break, okay?
Okay, thank you.
Amber, can we start?
Okay, let's start. There's someone need have a question. Before your question, this is the right DLE. It goes that way in differential liberation expansion that we reduce the pressure and then produce the gas, and then we have the gas to get in the gas chromatograph the composition and to calculate the Z factor and all of this. This is something I need to focus to tell you that I corrected, because the one that was the picture that was inserted was the CCE. So for the question, please.
Yeah, thank you very much. My
Uh,
question was regarding the two-phase status,
hmm.
where we had on those phase graphs. Those two-phase status, when the liquid or the hydrocarbon is in that phase, does it mean
You,
the two phases are mixed with each other, or they are separated? Or it's like an emulsion or something else? How is the status of this mixture when they are two phases, or they are two different liquids?
you
Um,
mean this picture, the phase behavior of this picture?
I can't see any picture. I'm not sure if it's. Are you
No, I
showing a
can
I'm
see.
slide?
I'm sharing the phase behavior. I'm sharing the screen. Do you see it?
Yes,
Mm,
yes, we can see.
no, I can't. So let me log in again. Just a
Okay,
second.
no, in the two phase, no, it will be separate, not emulsion, of course. So, as an example, if I have an oil reservoir, or let have an example on gas condensate. In gas condensate reservoir, the if we say that at reservoir condition at the pressure, as an example, for 1000 psi and 200 Fahrenheit, so it will be in totally in one phase gas. What will happen if we have in this fluid the dew point as an example at 3500? So with the pressure depletion of the reservoir to get this pressure below the 3500, so here starting from this critical point, the separation will happen, and I will have a two phase separately, liquid as condensate and gas as a gas phase. Okay, now it's clear. Hello.
It's clear, Amber.
Okay, I will continue with the presentation. Maybe if any one had another question at the end of the session. So, dynamic modeling, common challenges and solution. We here, I finished the rock properties yesterday, and the fluid properties, how you input the fluid behavior and the composition and all of that. And now I will focus on the some challenges and solution you can face in this phase after initialization. After I will finish the challenges and solution, we will go through the how the well inserted in the simulation model and how we control it. And after that, we will have some practical uh, examples of history match and a case study, and the project management slide if you want to make a huge project or a full field project and you want to manage. So the first challenge is that you can face something called nonlinear convergence error. So why we could have a nonlinear convergence error if we have time steps too large. So Imagine that if you have a time step that you want a simulator to calculate what happened in the cell, and widening or make the time step too large, so a sudden change in the cell will happen. It's a bottom line in reservoir simulation. You have to be smooth in geology, smooth in the time steps, smooth in everything. So you don't have to make it aggressive, or like yesterday I told you, transmissibility shock or permeability shock. Never. The model must be smooth, so no sudden change in the very big sudden. So as you as before the break, I told you that the simulator don't have input inserted by me. It depends on the input that it output of the neighbor cell. So a lot of iterations happened. So in if you as an example make time step too large relatively to the model run. So this sudden change will give a huge number that's far from the right one. It will We will have a lot of iteration, and maybe from the too many iterations, the model will not going to work, or will be very slow in running. All the
Um,
example that I will give. Hello,
now,
hello.
one question.
Okay.
So here you mentioned, I mean, I can see in the for the time step too large, um, I see this saturation pressure change too big for Newton to handle. So does this use only Newton-Raphson method for the iteration or no other methods?
This will affect the iteration. Yes, it will make a lot of iterations.
So does the model not switch to other methods of iteration, or it will only use Newton-Raphson method?
يعني I'm giving the example with the commercial software and how simulator work. So it for as I understand it, that simulator like Eclipse or something, and it used Newton-Raphson method in the iteration.
Okay, thank
Okay. So also, if we have a very steep relative permeability curves, so as I told you yesterday in the Corey function, you can smooth the curve as an example from the n constant. It's when you have a very steep or sudden change in the relative permeability, it causes a lot of iteration. The if I have a fluid that on the volatile oil, that gas is coming so too fast, it will cause a lot of iteration and a lot of non-linear conversion that happened. And I call it non-linear is like the mathematics. The non-linear means as a variable power 2, or two variables multiplied by each other, so it's called nonlinear function. So the mass equation is or the continuity equation is a non or the when it converted to numerical, it's a nonlinear function. So this nonlinear functions will go a lot in the simulation. So if you have this error in the when you make the run, go through all of this and smooth your model, especially in the you will see the time step, or maybe you will find in the connection or about the transmissibility or something as and the fault or something, a sudden change. So make it smooth. For the linear conversions, you'll find that many variables change in the continuity equation. Each equation will have a pressure, and then we will have a saturation. All of this change with pressure and time. So the model will solve it like matrices. So anything happen, or too much conversions in this, from if you have any shock or any sudden change, it will cause a lot of iteration, and maybe a lot of matrices will happen. So as much as you can, you have to make your model smooth in form of equation of state, or form of fluid behavior, in form of relative permeability and transmissibility and all of that, so you don't have any linear or non-linear conversion. That's the key word about that. Of course, if you have a broken connection or the cells not attached to each other, or this is from the geological model, it causes an this non-linear and linear conversion. If you have a sudden or a huge or large mobility contrast between the oil and the gas or oil and water, so it's related to the steepness of the relative permeability curve. So this it will make the matrices and the continuity equation and the iteration will suffer. The model will suffer, and sometimes it failed. So that's why I'm telling you, make it smooth. So how to reduce how you make it smooth, reduce your time steps as much as you can. Smooth the relative permeability curve, check the PVT tables, the capillary pressure also must be checked, and refine the grid near wells. Sometimes you can make, if you have a coarse and well around the perforation, so maybe the interface between the cells and the perforation and all of that, it could give some errors in the calculation. So you will see in the next slide something we used called local grid refine, that the perforation in the well that you will insert we must respect the resolution around it, so you don't have these errors in the model when model is calculating and make its iteration. Another thing in the upscaling, I mentioned this the first day. Do not forget to our role is to minimize the number of cells as much as you can, but do not forget the heterogeneity of the model. So if you make an upscaling in improper way, you can lose heterogeneity. That you can, as an I told you in the first day, you can average as an example 20 or 30 cell in one cell, and these cells have variable have differences in porosity or net to gross ratio. So when you make the coarsening this cells, you will have a non-realistic property. So take care of it. Take care of the direction of the flow and the when you make the upscaling also, that you know that the layers must have a directions. So when you make coarsening, you have to save this direction, not make not magnifying or coarsening the grids to lose the direction of the flow. The relative permeability and the capillary pressure curve are nonlinear. So if you have something called, as I told you, a shock in the relative permeability curves of or the capillary pressure, if you have something wrong in the capillary pressure curves, it will cause a lot of issues in the if you make an upscale. So as I mentioned yesterday, we have something called leverage J function, and I'm inserting it, and the capillary pressure will distribute depend on the permeability and the porosity. So when I make the upscale, the permeability and porosity maybe change significantly if I make the upscale in the wrong way. So the capillary pressure will have a problem, and of course everything will have a problem, that like the transition zone of the and all of this. In the LGR, what is LGR? It's a local grid refining. It's recommended to have this. Imagine that I have a model and I make I make the upscale to reduce the number of cells, to reduce the number of calculations that you have. But in some places in the model, I need a refinement cells. So, and it depends on the scope of work of the model. As an example, in gas condensate reservoirs below nearby the well bore, maybe condensation happens. So if I have a very big cells, it will not going to mimic this behavior. So I need to make the cell more refinement. So if any behavior happened in very short distance or around the wellbore, I need to simulate it. So in that case, I will upscale the model, but in the crucial part in the model, I will refine this grids. So maybe when okay, so here this is the example of the gas condensate. If I have, as I told you, if I have liquid dropout or gas condensate, all I have to do is to make this local grid refining around the wellbore, so I can mimic the behavior of the fluid. So I have to take care of four things when I make these LGR: the tiny time step to avoid something called the current Friedrich-Lewis condition. What is this? Imagine if we have a fine cells and a high time step. What will happen? The flow will change across the cell, and the time step will not يعني in a very big time step. So we could have a flow in the cell not recognized by the time step. This will cause an error. So when we have according to the grid size, I have to run with time step proper for this model. So if I have a high time step and small cells, it could make an error. So the time step will not going to follow the flow of the cells. So you have to take care about this if you are working with local grid refining. Another thing, if something called the diffusion or numerical diffusion, if you make a coarse in cells instead of refined cells or small cells, some maybe from the interaction or in the neighbor cells could have a problem in the interaction with each other. So you have to take care about the keyword here, make it smooth. And of course the well index sensitivity. When we put a well in the simulation model, have to take care that the productivity will depend on the cell size. If I made when I made this the cell refinement, so the well will produce from a lot of many from a lot of cells. This can give a behavior of production more than the real one. So I have to make something as the cells. I can make it in radial well form, so I can reduce the number of cells that is attaching or truncated with the well. So I can make around the well an equivalent radial well flow. It's a local instead of Cartesian, so I can I will not going to make a lot of cells in the wellbore in the simulation modeling. So also in the LGRs, maybe we have some problems in the equation of state that the phase behavior in small cells. So we are talking about many numbers of calculations according to the equation in each components and each pressure. As I told you, so a lot of calculations, a lot of iterations, a lot of matrices. Sometimes the model will not going to, the model will try to solve it, but at certain point the model will tell you a lot of conversion happened. I cannot proceed. This is for the LGR. And finally, something called lumping and delumping. As the upscale that we need to reduce the cells as much as we can, something called lumping. It's like the upscale, but in the fluid. What we do in the lumping, we according to as clever as you can as a reservoir engineer, so you can mimic the phase behavior and make it in zoom in or make it in more low. يعني you will decrease the resolution of the components. You will to make lumping. What meaning of lumping? So you will tell the model from C1, it's a component. From C2 to C6, it will be one component containing four, and we call it pseudo components. And from C7 to C17, deal it as one component. So we are what we are making now, we are averaging, we are summing, we are lumping each four components in one component. So in the equation of state, in the how it solves the equation, it will we will reduce a lot of calculation by that way, by lumping. The challenge here is to make it not accurate. So if you don't know what you are doing in lumping, sometimes it could be you will face a challenge in the fluid behavior of the fluid, that you will not going to mimic the real phase behavior change. So you need to know exactly the components to be lumped with each other, and after that the model or another simulators can delump. So if after production, the production will go to surface facilities, all of that need a full composition to take care of it in terms of planning, to make compressors, to make in the for separator and all of that. So why we are doing lumping? To save the time and the calculations. Why are doing the lumping? For surface facilities and production to know the structure, so they could have an in the forecast, have an expectation of the components that they will have at the surface. So that's the in the lumping and the lumping challenges that I told you, that each real component has its critical pressure and critical temperature and something called eccentric factor. So when we lump, maybe a fake component will happen. This will affect, of course, the dew point pressure, the bubble point pressure, and all the physical properties of the fluid. So, and this, of course, if I have a liquid dropout, if I have a condensation banking and liquid dropout, I have to take care of lumping very well, because in the gas condensation or the liquid dropout that will happen, the scope of work, or the aim of the work, will be the components. There will be the equation of state, the how the component change, and how the oil phase will come and will affect the productivity of the well. So in gas condensate, I have to take care of the lumping process very well, to neglect or to avoid any dropout prediction errors. And finally, of course, if I have in lumping and delumping, if I make lumping in the wrong way, sometimes I will have a phase, if a phase not mimic the real phase. So I could have a 40% or 50% oil, but in real I have 30% only. So of course, the phase will affect the relative permeability, as I told you. So in reservoir simulation, we are integrated with the rules are integrated with each other. Everything affects the other thing. So everything depends on other things. So you have to take care in each phase. So to neglect or to avoid any problem in the rock physics or geological model or something. So all the key word here, or the key is the make it smooth and make it realistic and make it simple. That's why I'm telling you that. It cause, maybe in the lumping, it can cause the viscosity errors and all of that. So here I finished the lumping and delumping and the non-linear and linear conversion errors that we could face. Also the upscaling and the LGR. And before I will go to a case study or something, the last thing that happened in the reservoir simulation is well control. That I have to put the wells on their location, and I can control the wells in the simulation by rate or bottom hole pressure or tubing head pressure, or wellhead, pressure. So you can control by rate, so you can simulate the pressure, or control by pressure and make history match by rate. It goes that way. But there is a very important thing imported in the simulation model called VFP tables. Simply and very simple, the VFP tables, it It depends on something called the nodal analysis. What is nodal analysis? Simply, if I have here the pressure on the downhole in the well, so I can expect the pressure at the wellhead, rho GH is very simple. And also, if I have reservoir pressure here as an example, 4,000 psi, and here 3,000, so I have delta P 1,000 psi. I can expect that I have a skin in this well. But what I'm concerning in reservoir simulation is that the vertical lift of VLP, or the vertical flow performance. From I have to put a schedule that at each pressure here in the reservoir, the wellhead will be figure. As an example, if I have here 3,000, so at the surface will be 3,500 if in case of gas. In case of oil, it could be 1,500. It's a schedule that I inserted. So when I make the history match, I will make the history match of the wellhead pressure as here, and here's the some curves that I made to make it understand what I mean. What if I have something like that I have, I made a model, and the in the model I have four charts: the wellhead flowing pressure, the water flow rate, the oil flow rate, and the gas flow rate. And the real data in black, and the model is in dot. And I'm matching I made here a history match. I'm matching here the wellhead pressure and the oil flow rate and gas flow rate, but the water flow rate is not matching. So what I'm going to do, I will go to check in my simulation the relative permeability curves, an example. So if I check the relative permeability curves, so I will smooth the relative permeability of water or increase it. So I will find the production of water and get the history match, and I can with this new relative permeability and all the geologic model and all of things, I can depend it because it's history match. Another thing, as another example here, if I'm matching almost matching the oil flow rate and the gas flow rate, but I can't match the wellhead pressure and the water flow rate. What does it mean? It could mean that I'm missing the aquifer in my model. But when I will do the aquifer, what will happen? It will cause a pressure maintenance, so the pressure will increase and match, and the water will increase and match. This is how the simulation and history match goes. Here, as an example, if I match the water flow rate and the oil flow rate and the gas flow rate and the wellhead flowing pressure not matching, so go to the VFP table that I told you. That the table that I inserted is not right 100%. It must be added so I can match the wellhead pressure. It goes that way. Another example, if I have if I matching the gas flow rate like here and the pressure, but I cannot match the water and the oil flow rate, so go to the absolute permeability. So here I need to check my absolute permeability to increase the flow of the reservoir, so the water flow rate and oil flow rate could match. And in that time, we will see the pressure and the gas flow rate, what will happen. The final example, as an example, if you see here the wellhead pressure and the oil flow rate and water flow rate, it has to match, and the gas flow rate can't match. So this means that the fluid property that I inserted has something wrong. If it's a black oil simulator, so I have to check the dissolved gas that I put from the CCE lab, or if it's compositional, so I have a problem in the equation of state here, but it's an oil, so it could be an oil black oil simulator, so I have to check the lookup tables that I inserted in the fluid properties. That's how history match do. So again, to recap what we have done until now, we talked about reservoir fluid behavior. It changed with the pressure, and after that we start to explain. I start to explain the CCE and how you can know the saturation pressure and the relative volume, so you can with the constant mass, so you can predict the density. That is an input in continuity equation. And after that, we talked about the differential libration expansion experiment and see the mimic the gas, the reservoir depletion or gas production of the reservoir in the lab, and get the gas out and make the gas chromatograph and calculate the Z factor and all of that, and to insert it in the model to as a viscosity, and that is already important in the continuity equation and all of that. And then we agreed that there is a black oil simulator and the composition simulators. The black oil simulator will take the data of the lab that I inserted from the schedule, but the compositional is different. When the pressure in the model decrease, the composition will vary, and each and something called the Gibbs phase rule, that by Gibbs phase rule, it is the degree of freedom or the number of the variables that present the fluid type, and the fluid, the number, the percentage or the number of phases that we have. As an example, if we have something like methane, so we have to express it by the critical pressure and critical temperature of the methane. But if we have it's methane in the one phase, but if we have the two phase, but if we have a lot of components, so we have to mention the pressure and temperature and the mole percent of each component. But the simulator cannot read it like this. The simulator need lab experiment results like constant volume depletion, so it can read the components change with the pressure, and will depend on the component. It will give you the percentage of phases gas to liquid phase. And after I make this calculation, it will make this continuity or mass diffusivity equation to convert it to numerical, a lot of iterations. So we have to take care about these conversions, and a lot of the iteration I have to minimize. So I have to make lumping the component, I have to make coarsening, and if below the or near the well bore, I could make the local grid refine on all of that. And the key is to make the model from geology until the fluid smooth. You have to make to avoid any shock in the model, so it can make a lot of iterations, so it can't continue. This is about the reservoir simulation. The last thing before I go to the case study called how we can make a project, how we can manage a project of reservoir of field integrated study IFS. As any project we must have a scope of work. So the first thing, when you have a model, do it with third party or do it by yourself, you have to mention the scope of work, what we need from this model. The second is the project planning. You have to plan to make the Gantt chart like this. As an example, you need a plan. So in this, and from the first and the second month, the data gathering, and then the geology must have their work, and in the dynamic must gather the data, and then all will work, and we have a data to make the history match, but come back again to the structure model to modify and petrophysical model and make a history match again, and then it will go that way until the final decision we will do the final decision. And here we will not going to have the most real model, but it's enough for me if we have the target of the scope of work from the model. Then in the project execution, as I told you before, that when the project execution, you have, as any project management, you have to mention that the reporting system will be like the deliverability. All of that will be, of course, in the scope of work, the deliverables, the tasks, and all of that. And when you execute the project, first you have, after that you will control it in time by Gantt chart, and then we will go through the milestone that I told you called the initialization. This is the how the dynamic and the static model will meet, to see the volume and the initial condition and the volume of the static model. If it okay, you will continue and make the forecast and the infill well and close the project. So this is how the project management of the simulation model goes. So finally, as in a case study, there is a case study in that I shared in the. It's a paper, you will find it on ABG with this ID. It's published for free. Here I will say the problem here that I have, if you see this anomaly and this anomaly, the reservoir that here the case study was in 1980s. We have this reservoir with this contact, and in 2011 we drill a well in this anomaly, and we found that the pressure depleted with the same contact. So this is and at that time, the pressure that we got from these wells on this reservoir, okay, sorry, from the pressure of the well of this anomaly was here. So here we have a problem that we have two reservoirs that communicating with each other, but in the same time the contacts between this anticline and this anticline differs. So that's what I told you in the first day. Do we here need to make a simulation model to understand and predict the infill wells and how we can deal with the reservoir? The answer is yes. And what here the scope of work of the simulation? The scope of work of the simulation is to mimic the pressure depletion and the motion of the aquifer, and also to know exactly, or as much as we can, the original gas in place that it's a gas reservoir, the original gas in place that remaining in this reservoir. This is the challenge and the scope of work that we in that time, that the challenge that we want to know. So it was a very complicated, and here is the role of machine learning, that we have done the static model with and the dynamic model, but to match. We trained the model to know how it can history match, and after that we do a millions of realizations. As an example here, this is the conventional reservoir simulation that I told you in this workshop, that will do the seismic, then interpretation, structure model, petrophysical, and dynamic, and the forecast. But what we have done here, that we do the same thing, but after that we make a machine learning that we made a millions of uncertainties and realization, and we put the uncertainties like the Fisher's distribution, the petrophysical parameters, and all of that, to get the realistic history match with this contacts. So why we use the machine learning? Because a lot of history match we have to do, a lot of runs we have to do to mimic the pressure depletion without motion of the aquifer. So it was a mess to have many runs and modification. So machine learned here do a lot of realizations and give me the best realization with the best matching volumes and best matching history match profiles. So, and finally I took the decision to take the realization that is okay with me in the geology of the field. So here I finished. I'm sorry, but I today I make it long, and I try to make it simple as much as I can, I swear. But this is all about reservoir simulations. Is how it works, and this is how you have to take care. So if you are working as an early career, I think it could be beneficial. Some slides I put, I know that it could be useful. If you are a student, so it's a very good opportunity for you to see how in the practical and why you are studying the relative probability, capillary pressure curves, and the mathematics and all of that. It's a part of the real world practical work. And if you, as a geologist, now I think you know about the dynamic, and if you are a reservoir engineer, you know how the static model is done. So you can go if you have something wrong in the history matching, or that you can pick the problem, where is the problem, and you go for it. So thanks. I finished the workshop, and I'm open for any questions. Hello? Any
Hello.
questions?
Yes, yes, it's me again. Sorry. Thank you
Okay.
for your presentation. Uh, one thing I think I need to ask you possibly, the when you are looking at history match,
Hmm.
um, so because I'm making the static models basically,
Hmm.
and that was very useful. Which part of it you mentioned about the fluid properties, and also you mentioned about the in fact a static model. So which part of it, when we are looking at, you usually see in the static models that you need to ask the modeler to refine or improve? Um, and for example, when I'm looking at the history match, you mentioned about aquifer, you mentioned about the perm, you mentioned about the other fluid parameters. So usually, which side of the story you usually ask the static modeler to have a look and improve it? Thank you.
Very important question, and very clear, and very good. So, as a reservoir engineer, doing dynamic models, the problem of static model could be it's more than يعني a lot of something you have to take care in the static model to do. The first thing, try to make it smooth for the reservoir simulate for the dynamic. As an example, in the rock types, or the in the layers and all of this, it's very good to mimic the real geology, but we are making simulators or static models, so it can for flow, not just for geology. Of course, you have a geology you have to respect, but also take care a lot about the number of cells and how it presenting. So it will make my life easy, but this will not affect the history match. Okay, but it will make my life only my life easy. This is the first thing. The second thing, the faults, of course, when you make the structure model, the faults must be done in a very proper way after structure framework I'm recommending. So the fault truncated with each other 100%, so I can't have any errors lately in the dynamic model when I make the run. Third, sometimes I insert the permeability, or you in the static model you insert the permeability as a function, as an example in porosity. So if I have something, and this is concerning the history match, if something like that, here the problem here in the absolute, why I told you the problem in the absolute permeability, because I have the problem here in the flow. So to increase the flow, obviously will make a depletion in the pressure. So the pressure will decrease and the flow will increase. So the permeability here, sometimes I use it as a function of porosity. So maybe in the static model, we put this function. We can edit the permeability as a property model. We can edit, or In the porosity, we need to make an averaging of porosity or distribution of porosity in another way, so we can make a better history match. For the aquifer, in the dynamic, we can control it using many numerical models. Sometimes it's called Vitkovich or Carter-Tracy, and it's the potential of the aquifer. It's a dynamic issue. Uh, and nothing for the fluid properties is always our responsibility. But concerning the static, I can go to the static, and I have an example here in the case study. You, you see that in this case study, as an example, the challenge was in the structure model that I have here an anticline. Here I have an anticline, and here I have an anticline. And when the water come up, in this anticline, depending on the saddle between these two four-way closures. So because of this saddle, the I have multiple gas water contact. So the game changer in this model was the depth of the saddle. So we make a modification in the structure models. So it depends, يعني. Sometimes I can refine or make some edits in the structure model. Sometimes I have to make a lot of realization or distribution again to make the history match. So it's about the flow and about the dynamics in the reservoir that may be it affected by the structures. Am I clear now?
Yeah, thank you very much. Yes, I understand. I think that those slides were very important. Thank you.
Thank you. So please, I need questions.
Yes, hello.
Hello.
I am a geology student, fourth year, and I would like to know what are the key elements I should focus on to make my work as relevant as possible and current for the engineer who will be in charge of the reservoir modelization and fluid flow simulation.
Okay, so I think the first day will be the most important. Will answer all your questions. In the first day, you will find the video on the Mega Plus channel. uh, all you have to do as a geologist, your homework is to know exactly the geology, study geology. I'm not talking about simulation. Study the geology of the field very well, local in your field and regional, so you can have a strong background and a strong concept of your reservoir, so you will apply. The concept is structural. The concept is the how the depositional happened. So you can distribute the petrophysical parameter from well that you interpreted, right? And the fishes also. So my advice is to understand very, very well your concept of geology, and in modeling, choose the right distribution method. As I told you, if you want to go through static modeling, you need to understand very well the variograms and how kriging work, and so you can make uh, two or three or many scenarios with sensitivity in kriging distribution to reach the best distribution you can do. And of course, if you have an anomaly or a gas channel from seismic, it will help you a lot in this distribution. You can do it by something called object based. So you can put the trend and make distribution according to the trend that you will see. Thank you. Am I clear? Answered your question?
Yes, thank you.
Because all of this will affect the volume at the and for me as a dynamic, I need the volume that I will match, and I will then do my dynamic according to your volume. Any question? Anyone had any question concerning anything?
Yeah, there was a time you spoke about the components, the phase and the degree of freedom. So I just want to know, like, if you have like gas, oil, and brine in the reservoir, so what would be the degree of freedom?
Okay, it's a very it's a question need an answer, but I will try to make it brief. Okay. In the Gibbs phase rule and degree of freedom, it's I need to know the number of variables that will express the components. As an example, if I have here a gas, only one phase gas with two components in one phase. So to express the fluid, I have to know the pressure and the temperature and the mole percent of one element. And when I know that, so I can know the percentage of the other element. As an example, pressure 4,000 psi, the temperature 200 Fahrenheit, and at this pressure and temperature, I will get 60% mole or 90% mole percentage of methane. So the percentage of the stream is methane 90%, and the 10% is ethane. Imagine that we have 20 component. What Gibbs phase rule said, in the 20 component, I will have pressure and temperature and 19 mole percentage, and the last one will be the rest of the 100. So I have to insert, or for these seven components, the mole percent at the certain pressure and temperature. Okay, and then I can, from the component, I can predict the liquid phase percentage and gas phase percentage. If you look at in the books, you will find that the liquid phase we express by y and the gas we express by x. So I can predict the phase percentage from the components. So this is how Gibbs phase rule and the degree of freedom is about the number of variables that needed to know the percentage of phase. As an example, I have from C1 to C5 mole percentage summation, as an example, 70%. And from C6 to C7, which is maybe liquid phase or at that pressure, so it will be, if I said the from C1 to C5, it will be 60, so it will be 40. So here I noticed that for the hydrocarbon, I have 40% oil and 60% of gas. For the water, it's about the volume, it's not about the components. So hope that I simplified.
Yeah, thank you.
You're welcome. Okay, any other question? Today is the last day, so any question for the first or the second or the third day, I'm open. Okay, that's it. I think I hope that the workshop is beneficial for you. You invested your time with me, and I'm very glad and appreciating you all. So please, if anyone need any question or want to see the videos again, Mega Plus YouTube channel, you can visit, see the videos again. And if any question needed, you can ask their page or my page, official page on LinkedIn. I'm open anytime. You will see. So if you want any advice about anything, I'm here, or Mega Plus here. So that's it, and I'm very happy to have this time with you, and hope to see you again in the upcoming workshops and courses.
Thanks a lot. Thanks for the session. It was really fruitful. It was helpful. We could learn something from you. Thanks a lot.
Yeah, thank you, Fanny. It's I'm really appreciate.
Thank you.
Thank you.
All right, this brings us to the end of our 3 days workshop. Thank you very much, Engineer for all the time you invested with us and all your efforts. Thank you for everyone again for participating with us in the 3 days workshop. We can't wait to meet you all in our upcoming workshops and courses. Have a good day, everyone, and goodbye. Thank you.
Thank you. Bye bye.